endowing robots with longer-term autonomy by recovering from external disturbances and manipulation through grounded anomaly classification and recovery policies. As part of our Sense, Plan, Act, Introspect framework, we use a manipulation graph for task representation. The graph is composed of nodes, which in turn are composed of 3 modules. The motion and visual modules encode manipulation skills and corresponding goals. The introspection module uses non-parametric Bayesian statistics with advanced variational inference to identify and classify anomalies globally in the task. On top of our framework, there is a novel recovery critic that enacts contextual recovery policies in the presence of anomalies. Motion generation technique, dynamic motion primitives were used here. One-shot demonstrations are used to encode motor skills for motion modules in a kitting experiment. The training also helps to establish visual goals and nominal models for robot introspection. A collaborative kitting experiment is conducted through a Baxter humanoid robot. A human collaborator places common household goods in the collection bin of the robot. The robot then places the goods inside the packaging. Here you can see how the initial task graph is bootstrapped through raw smash. Nodes, modules, and our framework functionality, however, occur in the background beyond the standard smash formulation. It is possible, as part of our collaborative task, for the human user to disrupt the robot's environment in unintended ways. Here we present 4 anomalies that were originally discovered in our cataloging experiments. Reenactment is a task-level recovery policy where reenactment goal nodes are assigned through multinomial distributions that model human user goal node selections given a current node and a specific anomaly as seen in this graphic. Reenactments are used when accidental one-off policies occur. Adaptive policies resolve persistent anomalies that cannot be solved by reenactments. We rely on human intuition and expertise to provide adaptation skills through kinesthetic teaching. Here are 2 such examples. We now show an example of experiment 5 where accidental and persistent anomalies occur in the kitting experiment and where reenactment and adaptation resolve the anomalies. An introspection report window is shown each time an anomaly occurs to inform the viewer of the anomaly type and the executed recovery policy. Here we have seen how a tool collision occurred followed by a reenactment. And then there is a human collision followed by another reenactment. Thereafter, when there's a wall collision, there's an adaptation that lifts the bottle over the wall of the package. Once the bottle is tried to be placed inside the box, it experiences a tool collision that occurs with another object, and then another adaptation resolves the final anomaly. We now show an example of experiment 6 where both accidental and persistent anomalies occur during an already executing adaptive recovery. The aim of this experiment is to show that our system can robustly run an around-the-clock introspection and recovery system. In situations where more than one object may be closely stacked, it is possible for the pick skill to experience persistent anomalies. We saw such instance in experiment 5, at which point an adaptation was taught. Here, however, an additional object is also placed nearby, causing the adaptation to fail. In this case, a new adaptation can be taught to resolve the condition. The next example shows how after an adaptation to a wall collision, an object slip is induced. The recovery critic then activates a reenactment of the pick skill. In this instance, the visual module updates the skill goal with the current pose of the object of interest. This enables the robot to re-pick the object and place it in the box.